In the last video, we saw that substitution reactions can proceed through two different mechanisms, an SN1 or an SN2 pathway. In this video, we'll look at the reaction features that determine which pathway the reaction will proceed through. And there are four key features for us to consider: the electrophile, the nucleophile, the leaving group, and the solvent. And we'll look at one at a time. So first, let's consider the electrophile. The carbon that bears the leaving group must be sp3 hybridized for a substitution reaction to proceed. Second, as the substitution of the electrophilic carbon increases, the propensity towards an SN1 type pathway increases. And this is because an SN1 pathway proceeds through a carbocation intermediate. The more substituted the electrophilic carbon is, the more stable the carbocation intermediate will be. This means that primary alkyl halides will proceed through SN2 pathways. The resulting carbocation would be too unstable for an SN1 pathway. And on the other end, tertiary alkyl halides will proceed through SN1 pathways. The electrophilic carbon is too sterically hindered to undergo direct attack by the nucleophile for an SN2 pathway. But secondary alkyl halides can go through either pathway. And we'll use some of the other reaction features that we'll see in a moment to determine if SN1 or SN2 is more likely. The second reaction feature to consider is the nucleophile. And this is important for SN2 reactions. In the SN2 reaction, the nucleophile directly attacks the electrophilic carbon. And so a strong nucleophile is necessary for an SN2 reaction. And in general, nucleophilic trends will parallel the basicity trends that we've learned. An anionic nucleophile will be more nucleophilic than a neutral nucleophile. And moving down a column of the periodic table will lead to a more nucleophilic nucleophile. Third, we'll consider the leaving group. And a good leaving group will be favorable for both SN1 and SN2 reactions. But for an SN1 reaction, a good leaving group is required. Remember that the first step of the SN1 reaction is the leaving group leaving. And so if the electrophile doesn't have a good leaving group, then it won't leave, and a carbocation won't form. So a substitution cannot proceed through an SN1 pathway without a good leaving group. And here I've just indicated some common functional groups and their leaving group ability. And most of what we'll see is the use of alkyl halides as leaving groups. But we can also use alcohols as leaving groups if we make them better leaving groups. And one way to do that is to turn them into tosylate groups, abbreviated OTS. A tosylate is the structure shown here, and we can make it from the substitution reaction of an alcohol with tosyl chloride. The tosylate anion is a good leaving group, so this method allows us to convert an alcohol into a good leaving group. Another way to convert an alcohol into a good leaving group is to protonate it. Then the leaving group is no longer OH-, but instead is water, a much better leaving group. Okay, finally, we'll look at the reaction solvent. Polar solvents will be important for both SN1 and SN2 reactions, but polar solvents can be either protic or aprotic. And a protic solvent is one that has the ability to donate a proton. Acetic acid is a protic solvent. I have a few examples of common solvents here, and I'll encourage you to pair the structures with the common solvent names as you encounter them. Protic solvents stabilize the nucleophile, and that disfavors SN2 reactions. A stabilized nucleophile is a less reactive nucleophile, and in an SN2 reaction, the nucleophile directly attacks the electrophile. So when the nucleophile is stabilized by a protic solvent, is less reactive, the reaction becomes less favorable. Okay. Protic solvents also stabilize cationic intermediates, and so they favor SN1 reactions. Remember that SN1 reactions proceed through a carbocation intermediate. When that intermediate is stabilized by a protic solvent, the reaction becomes more favorable. So in general, protic solvents will favor SN1 reactions, and polar aprotic solvents will favor SN2 reactions. We'll end this lecture series with the question we saw at the beginning, to draw the product and transition state for the SN2 reaction shown. We can note here that we have a primary alkyl halide, so even if we weren't told that it's an SN2 reaction, we should be able to discern that because primary alkyl halides will proceed through SN2 pathways. Okay, the alkyl halide is the electrophile, with the iodine as a leaving group, and the pyridine with the lone pair on nitrogen is the nucleophile. So remember that the SN2 reaction proceeds in a single step, and in the transition state, the carbon nucleophile bond forms and the carbon leaving group bond breaks. Here we form the carbon-nitrogen bond as we break the carbon-iodine bond. So the transition state shows these bonds that are breaking and forming as dotted lines. And here the iodine has a partial negative charge on it. The electrons in the bond are moving toward iodine. And the nitrogen has a partial positive charge. The lone pair is moving toward the carbon to form a new bond. And in the final product, we have a new carbon-nitrogen bond. And be sure to keep track of your charges here, because the lone pair on the pyridine attacked the electrophile and formed the new carbon-nitrogen bond. And that leaves the nitrogen with a positive charge here.